usage. So basically, if you look at that required, okay, so this is a syllable.
Yes.
If you follow, I have started very briefly about wave, right? But do you want to discuss the further about wave, or do you want to go to we also have covered a certain amount of electricity?
Yes.
And so photon electric effect, right? We discussed the photon electric effect. So what shall we discuss? Shall we continue to talk about the wave or electricity, or shall we go to atom?
What's in the natural world? Because I think we don't really cover that in.
Well, natural world, you have to understand the British tradition. See, the Newton they built his name, or Newton built his fame rather based on studies the solar system. Because before Newton, nobody know why the planet orbit about the sun. Okay?
Yeah.
So Newton is the first to study the solar system. Can you see? So that is a British tradition. You see, it's a prime because Isaac Newton was the first person to understand that all planet, even including star, will follow this his gravitational law. Can you see?
Yes.
So that's why natural world is including, the atomic world. The small side is atom and molecules, right? But in physics, we only study atoms. Okay, molecule belong to chemistry. Right?
Yes,
and,
I think I studied the models for like 2 or 3 years. So I think I'm quite familiar with that.
Yeah, yes. In that case, we can skip with the Bohr model. All right.
Yeah.
And Bohr model is it's required. Do you know how to derive the Bohr model? Energy formula in Bohr model.
What does it mean specifically?
Yeah, so we can, before perhaps I can ask you the question. So in Bohr model, so what is a Bohr model? I think I noticed that it's required in this test. And basically, so what is a Bohr model? So if you have, do you know the formulas? So the Bohr model can give the two formulas. One is the formula for the radius. Okay?
Oh.
You know this formula 1, 2, 3. That is called a radius model.
Oh, I didn't know that.
Another, yes, this is simplified formula. The A is called, this is the smallest Bohr model. This is small. So basically, if you draw this graph, if you put this for the hydrogen atom, right? If you put a proton at the center, I'm sure in chemistry we use Bohr model all the time. So basically, the n equal to 1 will be the smallest. You see?
Yes.
And if we just draw this without proportion, we don't use the scale. We just draw another one. This is 2. You see?
Yes.
So this is Bohr model. And how much do you know about Bohr model? Tell me. This is a proton. This is a proton, and electron for the hydrogen. There's only one electron, right? Yes. So before Bohr's that there's no theory about hydrogen atom. Hydrogen atom is the simplest atom, smallest as well. So how do we work out? How do we describe the hydrogen atom? That was a very challenging question in towards 1920s. And Bohr was the first to work out the formula. For example, this is the smallest. This is radius, right? And also this formula apply for other. So the second radius is this one. You see, and so on. So because n is integer, so you can just pick up any integer continuously, consecutively, right?
Yeah.
So this is electron. This time electron is orbit about the proton. Okay?
Yes.
So in chemistry, we just use Pauli exclusive principle. we know that there are only 2 empty places for electron in the first shell. Right?
Yes.
Second, I got 8, right? And this is a radius. So basically, Bohr model. Can we still write his name properly? Bohr's model, Bohr's atomic model. That is that is part of natural world, okay? Because that is so Bohr model is the first is radius, okay? So R is a radius. So this formula is called the radius. But radius is just one of formula. We barely use this formula. Another important thing is energy. So Bohr model also gives you the energy, okay? The energy of electron in the hydrogen atom. One moment. Energy. For electron, for the hydrogen atom is the total energy of both for hydrogen atom. But actually, yeah, it's just for the hydrogen atom, it's including electron and proton. Hydrogen atom. That is very important formula. For this test, you're going to use this formula. The formula can be written as simply, if we forget about it, we just write numbers, right? If we just use numbers, that is a number for this energy level. This is n squared. In this case, the unit should be EV. So what does that mean? This means the energy is not continuous inside the atom. Energy is not continuous because before Bohr, the classical theory, both Newton's and Maxwell's electromagnetism predict that if there is only one, by the way, the interaction between these two is a Coulomb force. Can you see? Attraction between the two is a Coulomb force. One is positive, one is negative, right? So that is according to the classical physics. And the energy level is continuous. However, according to Bohr model and also based on experiment observation, this energy level, any formula is not, by the way, n is also equal to the integer, positive integer, you see? So based on this formula, you can see the lowest energy. The lowest energy will be, we just use as a color. I can use a white color, right?
Does the n mean which level the electron is at?
Well, which level is available? Electron can be any level depending on the condition. An electron can stay in any level, but if the ground, the lowest level is the most stable. So in many cases, electron, when atom is free, and you will find the electron is on the ground level.
Yeah, so that's the energy stored inside the atom. So as the electron moves away from the center, its energy gets lower.
It gets lower, yes. That is if you use Bohr model. If you use Bohr model. But Bohr model is based on the particle, right? We're still talking about, can we draw a few energy diagram here? So they just draw a few of the energy level. To my pen. Okay, this is just example. This is n equal to 1, can you see?
Yeah.
N equal to 2, n equal to 3, and so on. And n equal to 4, can you see?
Yes.
So eventually, by the time here is n is approaching to infinity, can you see? In other words, electron will if electron can go out, then this electron will become free.
Yes.
So on the this lowest is called the ground state. So electron often stay here because most stable.
Yeah.
Okay, this is just like a mountain. You see, if you have if you got a mountain like this, right? So the object will be most stable in the lowest position.
Yeah.
Okay. However, if the that is very important formula to understand the experiment. If you have a photon coming, you see, photon will carry out a certain amount of energy, do you agree? According to Planck. And the interaction happens, so electron can absorb this energy, okay? If this condition satisfy, the electron can jump to the adjacent, the higher energy level.
Mm-hmm.
So if the condition satisfies, so if the any amount of energy of photon is, in this case, is exactly equal to the energy difference between second, this is called the first excited energy. This is called the ground state energy.
Uh-huh.
Can you see that one?
Yeah.
That is a condition for absorption, you see.
Yes. Does it have to be a photon?
Photon carry energy, yes. And if the good question, if they have another particle coming, and they may also randomly excite electron. For example, during a chemical reaction, right? Yeah. When temperature increase, and also you put some chemical acid, or it depends on acid or base, and the atom will be ionized. Can you see? Mm-hmm. And that is due to the condition. Okay. Yeah. Electron also will be disturbed by the condition. Okay. But for the photon, that this absorption is selected. So this is called the resonance condition. Have you heard of resonance condition? Resonance.
No.
Resonance absorption. This just selectively absorb energy.
Oh.
At a certain frequency of photon. Okay. So this is a condition, all right? So the condition were determined whether at what frequency electron can jump between these two energy level, right? But in general, so this is a special case. In general, electron can go also from here. Electron can go from here to other energy level. Can you see?
Yeah.
Can you see that?
Mm-hmm.
So that is I can use a purple color to highlight this one. I use I use color, I use a red color. I will tell you why. And this is called the green color. Okay? I will tell you why I use a different color. And this is a purple color. Can you see? Yeah. Color can be represented by frequency. Do you agree?
Yeah.
So this absorption. So between any energy level, electron can jump. All right. Once they absorbed energy from photon, they can jump selectively, right? So what happens if let's just consider the experiment part. Okay? If this is a source, okay, this is a light source, right? This could be the sun. So this is a source. So this is a light source, or if you know, you tell me, all right? If you haven't heard of this background, we better to understand this first, all right? So if you put the hydrogen gas here, so that is how you put the hydrogen gas here. Can you see? Can we say this? This is a hydrogen gas, okay? Yeah. Of course, hydrogen gas is made by hydrogen atom, right? Yeah. So I just draw a single atom over here. So you can see that this atom is a distribution. This is a sample. Yeah. So you put the light in between the sample. So basically, the light will come in for that direction. If you leave the hole here, right, the light will come in, and interaction will occur between photon and electron, right? Yeah. After that, you can see some transmission. All right, this is called a transmission, right? So that's the incoming, that's the translation. And then what you can do, you can use a prism. You see, do you use prism? Can you see?
Yes.
If you use a prism, Newton did that before. So we can see the spectra. So in other words, I don't know if you have studied this part. So the white colored ray, which is transmission, right, will be burned at a different angle. And this is this is different from diffraction. It's called dispersion. Have you heard of dispersion?
No.
You change your direction, similar to the this is similar to the diffraction. Okay. And then color will, so they have different wavelengths or different frequency, will give the different angle. Okay. So that is Newton's experiment or experiment method. You can see that is a rainbow-like. If I just change the colors, you see, I change the color. See. So that is how we can separate the white color into different color. So this is this experiment is called spectrometer. Do you know spectrometer?
Yes.
Spectrometer is used to obtain the spectra. That's called a spectrometer. Okay, I just draw a few. Let's just draw other. What happened? No.
I think I get what you're saying. Is it the specific wavelengths of light absorbed by the
yes.
transistor?
They can only absorb specific light, not all. Can you see? So basically, you can see that this light beam can be spread into different color. Okay.
Yeah, but missing some bands.
Yeah. So if I just continue draw, if I just draw the result here, so the result is this. You can get the This is called a spectra. Okay. It's called a spectra. So spectra can write down here. It's called a spectra, absorption spectra. Okay, this is absorption spectra.
I've learned that one.
You know this before. Okay, spectra. So what happens is that if without the hydrogen sample, then you will get this. Let's just do it very. Yeah, it's very useful, this diagram. So you got the red color here. Okay. They got this rainbow-like. So they got this rainbow-like. You got the origin color. And that is white, yellow. Yeah, that is, I will use this diagram to give you a formula. You see, so that's why. Okay. So that is green, and you got the blue. And that is called a visible light. Yeah, oh, this is part of your knowledge. You need to, this is part of the electromagnetic wave spectrum.
Oh.
We are going to know all these names, which is required. For example, this is this is called visible. This is called the visible light. So this region, this region is called, oh, I just change the color. So this part is called visible light. Okay. Visible by our eye, it's visible. And do you know what is this side? How about this side?
The other side is ultraviolet. Yeah. Oh, infrared.
Infrared, it's called infrared. Okay. So it's ultra UV. That's the UV on this side. Okay, today we're just focused on visible light. Okay. So once you put the hydrogen here, I just draw that some part of in the red color will be disappeared. Can you see? I use a dark color here. So can you see dark color here? Just something we're missing. Can you see? Can you see the red dark one?
Yeah. And
similarly, some green color they will also disappeared. Can you see? And that particular frequency and that just continue. Can you see? And this is the green color and the purple color. Can you see? There are more and more on the purple color. Can you see?
Yeah.
So that eventually they were getting very clouded. Okay. So that is a spectrum of the hydrogen absorption spectrum. And emission spectrum also gives the same pattern, but it's just opposite. This is like it's called absorption. So some photon is missing, can you see?
Yes.
Absorption. Now, this experiment has been done before Bohr's, right? Many years before Bohr's theory, this experiment has been observed. But the question is, how do we describe the wavelengths? Oh, by the way, this is wavelengths, all right? For example, how do we describe these wavelengths? Can you see?
Yeah.
And also this one, and this one. You see this one? Of course, if I use this color here, you know that each transition, each dark bar, darker line will associated with the two energy level. Can you see? This particular transition group calls for Balmer. You know Balmer transition?
Maybe. I think
yeah, it's Balmer. Yes, Balmer transition. That means it's just the person who first observed this transition in the visible light from hydrogen gas. Okay. Now, if you know that theory, can you write the formula for these wavelengths? Can we say if this is 1 over lambda? Any can we call this? Can you write the formula for that? Do you remember? Can you write the formula? Say the red color one. Read the color one. Can you write the formula for this? Do you remember?
No, I only know that there's many types of transition.
Yes, many series called Lehman, and Balmer, and Balmer is invisible. Okay. Now, I tell you what, before Bohr model, this model was put forward, as I mentioned, that is in 1923. All right. However, this formula was proposed by other scientists earlier. Okay, so they have the formulas. For example, Balmer have the formula, and also do others. Can we just write the Rydberg formula? R for Rydberg. Okay, this formula will tell you that this formula can be written as n squared take m squared. Do you know this formula?
No.
I think you need to learn Bohr model. Okay, this is experimental. This is called empirical formula. Okay.
Yeah.
And this formula just gives this is called Rydberg. The Rydberg. So Rydberg, write down his name here. R for Rydberg. This is Rydberg. And he got this formula, okay? Of course, he's not the first one. He just modified Balmer's formula. Balmer is first, okay? Anyway, so this formula, can we just write down here, just put M here. I just rewrite this part. Can we just differentiate that? Can we call it M? Can we use a subscript here?
What does it mean?
That makes sense, okay? So that means that this transition, can you say the red one? Can you say the red color one? The red color one, that would be called lambda 2, m equal to 2, and equal to the constant. Very simple formula. Can you see this is just how to say formula for resistor in parallel. You see, it's very similar. If I just clear up this one a little bit. So this formula can be simply written as this one. And that is n larger than 2. So n equal to that one square, take that 2 square, m equal to 2. Can you see?
Yeah.
So n is larger than that. So n from 3. So n is not 3, 4, 5, and so on. Okay. Can you follow me?
No.
No, so this formula tells us that if in this, so Balmer transfers this, including all this color, okay, in the visible light. The first line is red. Can you see?
Yes.
That makes sense now. The second is probably the yellow or green, very close. Can you see? Sorry, this is 5. This is 5. So if you jump to the 5, can you see?
So it's the level which the electron jumped to.
Yes, but people didn't know. But now we know, now with Bohr model, so that's why Bohr model is very important formula, all right?
Okay.
More important theory. And also does this purple one, can you see? You can imagine that without the Bohr model, people only got this stuff. Can you see? They got this Rydberg formula. They got this Rydberg formula, all right? And which can also, they can use this formula to explain the experimental result. Can you see that?
Yeah.
So it's great, okay? They can explain, they can calculate that, they can use the formula to describe the observed, this called a barcode. You see, like barcode, like in supermarket, each goods has barcode. So that's very important discovery. However, because at Balmer and Rydberg's time, which is in 1800, and nobody could explain why the atom gives this strange, it's called a discrete absorption. Okay, it's called a discrete or nine absorption. So the you can call it the nine absorption.
Yeah.
Or you can call it discrete mathematically, right? Discrete absorption. So whenever you, because this is strange in classical theory, the energy can be continuous, like a kinetic energy, right? Kinetic energy can be any value, but in this particular, that the transition, they only absorb a certain amount of light. However, after Einstein, so this is why Einstein, if we combine the Bohr model with Einstein, and things became understandable, can you see? So this is a Bohr model plus Einstein's formula, you see? According to Einstein, the photon energy, can you put a pH for photon, right?
Yeah.
Photon energy can be written as a constant multiplied frequency, right? And also it can be, if you just convert frequency into wavelengths. Do you remember this formula?
Yeah.
That's just 1 over lambda. Okay. Yeah. Can you see that? This is 1 over lambda apart from the constant here. Can you see? Okay. So how can we explain? So this is a Rydberg formula. This is a Rydberg formula. How can we explain this formula? Can we just copy? Can we just I show you on this single page? Okay. So this is Einstein's formula. That's the energy. Okay. Energy formula. This energy formula photon. So if I just borrow the idea from photon effect, electron can absorb the energy from a photon and jump. Okay.
Yeah.
So that's why the energy, depending on where they landed, of course, if energy is sufficient, they can actually become free. You see, if electron goes that one, that will become free electron. They have escaped the proton, the free electron. Anyway, how can we use this formula, Einstein's formula or Planck's formula, to explain this condition? We'll probably go to simple single page. So basically, we have this. This is a Rydberg formula, right? Rydberg formula. That is that's just based on observation. Okay. That is lambda equal to a constant r and 1 over n squared. Take another integer square in m squared. Can you see?
Yes.
And if you use energy formula, Bohr model says that according to Bohr, okay, Bohr model is very important. Bohr theory, Bohr model, Bohr theory, should I say? And we know that energy of hydrogen atom can be written as integer. You see, which is just 13. Can you see? Is a number. Of course, if you want to know more, we can derive these numbers. All right, we can show why this number is at 13.6. All right, and in addition, we got Planck's formula. Okay. We got a Planck's formula, formula for energy, for the photon. Yeah. formula. So the photon energy, we use this formula by Einstein. Einstein used this formula to explain the photon electric effect, right? HF, or it's HC over lambda. Okay, now if you combine these two formulas, we can argue that the photon energy absorbed by electron, you see, photon energy is absorbed by electron. Electron uses energy to jump, can you see?
Yes.
So the required energy for jump is difference between the two energy level. I use a simple notation. Can you see that? So this is similar to the photon electric effect. Do you remember? In the photon electric effect, the energy is transformed into the kinetic energy of electron plus the work done. All right. But this one, in the absorption, the photon energy is not strong enough. Electron cannot escape from atom. So this photon electron effect is for electron has escaped from the atom. Okay. So how can we use this formula to explain the one experimentally obtained? Oh, it's very simple. What we can do? We just multiply. Can you see? We multiply HC. Can we? This part became HC over lambda. Can you follow me?
Yeah.
And this part will become R multiplied HC. Depend on n squared. Can you see?
Yes.
Take the m squared. And from here, from this formula, we know that these two is nothing but exactly equal to
the change in
change in the change. Can you use it? If you use delta sign, that will become RHC and n squared. Can you see?
Yeah. And
of course, we have put a negative sign here. So from here, we can directly obtain that the RHC is exactly equal to 13.6. Can you follow me?
Oh, so R is also a constant.
Yeah, R is a constant. This followed by readable R. So he's but we don't. People didn't know the meaning until the Bohr put his theory. Okay.
Yeah.
So this is Bohr model. So Bohr model can be used to explain any absorption line by hydrogen atom. Can you see?
Yeah.
Because if you have time, we can go further to how to derive this formula, right? So basically, do you want to derive the formula now? Or
I'm not sure what does the rest of the formula mean.
Yeah. So if I just stop here for a while, we just make sure if you just read that. If you just read that required the syllable, it's called the syllable, can you see?
Yeah.
And yes, indeed, can you see? That paragraph show you need to know the Bohr model of atom, can you see?
Oh, yeah. We studied the model, but didn't include those formulas and calculation stuff. So
you know that Bohr, obviously in chemistry, you know that Bohr has done something called the Bohr model, right? And in chemistry, we only use some part of his formula, right? In chemistry, we are more concerned the electron configuration of different atoms.
Yes.
We use Bohr model to fill the electron, right? We know that how many electron can occupy specific shell, right? But that is not Bohr theory, though. See, it's not Bohr theory. Yeah, if you're interested, I can go further. For example, is part of your you need to know in order to take this test. If I just show you how to do this, can you see? I just go to I just going to go to new page here. let's just do it. Let's just work out how Bohr work out his theory. All right.
Yeah.
And that is some theoretical study. So we got the proton here, right? We got the proton. By the way, which experiment in history allowed us to work out the solar system model for atom? Which experiment?
Sorry, to work out the.
How did we know nuclear exists in atom?
I don't know.
You didn't study the history? So
Yeah.
this is this Bohr's experiment is based on the Rutherford. You know the Rutherford?
Oh, the golden foil.
Yeah, golden foil,
Yeah.
the Rutherford experiment. Before Rutherford, and everyone say Rutherford. Before Rutherford, that everyone thinks that the atom is like the plum pudding. You know the plum pudding?
Yes.
J.J. Thomson's model.
Mm-hmm.
But Rutherford, this is called alpha particle scattering. They use alpha particle.
Yeah.
And it also is useful to know because this alpha particle is actually the helium nuclei. Okay. So our alpha particle scattering experiment, collision, okay, scattering experiment. That give us the model of nuclear. The proton is the center, right?
Yeah.
And the electron is here, so there's electron. And the distance is r. According to Coulomb's law, so that's electricity, okay? So first the starting point is Bohr uses Coulomb's law, okay? So there's a charge between the two charges, is positive, right? And negative, the Coulomb's law. Coulomb's law say the force between these two particles is equal to the constant multiply E squared, because both got a charge of electron, okay, and divided by R squared. So the first equation to build Bohr model. Okay. And the second equation is Newton's second law for circular motion. Do you know that? Do you remember Newton's second law?
Yes.
Yeah. So that's Newton's. So Bohr still use classical theory. Bohr still use the classical theory in dividing his new theory. Okay? You develop his new theory. So basically, the centripetal force, right, were equal to the mass of the electron here, and multiplies V squared divided R. Do you know this formula?
Yes, I've learned it.
Yeah. So if you combine these two formulas, so we will give that the Newton's law says that is a force K E squared R squared will equal to M V squared R. Is it?
Yeah.
Now,
Why is the centrifugal force equals to the force between proton and electron?
Yeah, the Coulomb force. So that is what is? Did you ask what is force?
Why are they equal?
Oh, because the charge of electron and the charge of electron are equal. Are you asking the electrical charge, right?
I'm asking why is the Coulomb force between proton and electron equal to the centrifugal force?
Oh, there's no force. There's no other force other than electrical force. When you put the two particles together, charged particle.
I mean the centripetal force.
Yeah. Because it got attraction, do you agree? Without attraction, electron will escape.
Yeah.
So that is why that's important. That is Newton's idea that there must be attractive force between these two charges. So not Newton's, but the Coulomb's force. And the reason why this electron can move in a circle, that because we use the solar system. That's why you can see after you study atom, you need to study solar system. But in history, we know solar system first by Newton, right? Yeah. So Newton knows that because gravitational force is attraction, right? So that is why Newton proposed that there must be exist the attraction between any two mass point. Okay, so that's why Newton had successfully explained the solar system.
Okay.
That's his contribution. But when we study with tiny particles such as a hydrogen atom, we have no reference. Therefore, people can only assume perhaps if the force is a Coulomb force, then that force can acting as a centripetal force.
Okay.
So that electron can orbit about the proton.
Yeah.
Because according to Rutherford, all the positive charge is located at the center of the atom. Do you agree?
Yeah.
So that is the first idea. So we are of course, it's non-story. If you want to know the little bit of his history, that before that, the atom is considered as just what is atom? Atom is just the Bohr, according to Dalton, right? You know the history of Bohr. So this atom is just the Bohr, you see?
Yeah.
But then after that, we came up, just draw this Bohr here. So this is the Dalton's atom, just like different Bohr. And then after the J.J. Thomson, then the electron became atom became the plum pudding. You see, so that is a bit of history. If your teacher didn't tell you, that is a history. This is called Dalton's atom. You see, Dalton. You know Dalton?
Yeah, I think I learned that in year 10.
Yeah, Dalton terms. Yeah. This is J.J. Thomson. Okay, this is J.J. Thomson. Yeah, history will help you. Because this is a very small world. You know who is Rutherford? Rutherford is one of the students of J.J. Thomson. Yeah. It's called something wrong with my pen. Thomson. Okay, so that got this as a plum pudding model. So the electron is evenly distributed, can you see?
Yeah.
And this orange color represents the positive charge, can you see? But when Rutherford came, they said, well, no, the positive charge should at the center, okay? So electron is orbit about the nuclear, can you see?
Yeah.
This is just and they have no assumption, they have no model, except they can just maybe it looks like a solar system. Can you see? That's why you see this type of drawing of atom. Can you see?
Yeah.
This is Rutherford's atom model.
Is that what he gets from the golden foil experiment?
It is what?
Is that what he gets from the golden foil experiment?
Yes, because if they assume the positive charge is everywhere and the alpha particle cannot be rebound, can you see? Only this can we do? Yes, good question. If I use a alpha particle like this, okay, in this time the alpha particle can be if this distance change, can you see? If this distance change, can we consider alpha particle come from that direction? Can you see? If the alpha particle originally here and they only change the angle slightly, can you see? And if this angle, if just towards that, if this case, the angle will change slightly larger. When they're getting closer, the angle will probably change like this. Can you see? And if this heat on, there will be rebound. Can you see?
Yeah.
However, if you use the Thomson's model, okay, if you use the Thomson's model, then the alpha particle can just penetrate completely. Almost no deflection, can you see?
But why is it deflected? Is it because of the electron?
Well, if you're interested, I build the model for you, because basically because positive charge is everywhere. Once the particle enter to the certain area, only inside a positive charge will affect this alpha particle. Because if you assume this orange color represents the positive charge everywhere, right?
Yeah.
We can discuss this issue next time, all right?
Okay.
Because we're trying to work out this formula for you. This is the key. It's more important because unfortunately you didn't know this history, right? I show you. This can be proved, right? So basically, it's called the alpha scatter experiment. So this is alpha particle. You see, they are all alpha particle with a certain kind of velocity. If we use J.J. Thomson's model, we cannot get this large angle. Can you see this is called angle of the scattering? Can you see? In this case, in this particular case, this angle is almost 180 degrees. Can you see? But if you use J.J. Thomson's model, the scatter angle is just a few degrees, probably 5 degrees. That's all. And if you don't use the if you only use J.J. Thomson's model, the scatter angle cannot larger than 5 degrees, but experiment show that the angle can be as large as pi, 180 degrees. You see?
Yeah.
In history, that is how the Rutherford's model is replaced by J.J. Thomson's model, his teacher's model. Does it make sense?
Yeah.
Okay, we just accept. If you're interested, we can discuss how this experiment work. But today we started from halfway. Can you see? We just assume Bohr believes that Rutherford's model is correct because Rutherford's model is based on experiment, okay? Where J.J. Thomson's model is based on his imagination.
Yeah.
So that's why if we continue, can we rewrite this formula? We will have, we got R on both sides. Okay, we got R on both sides. So we got R and E squared, okay? Divided by R, we're equal to V squared, MV squared, can you see?
Yes.
So that is an important formula. That is the classical formula, right? However, from here, Bohr made some assumption. Okay, that is a Bohr's new assumption. It's called the Bohr's condition. That's Bohr's quantum condition. Quantum condition. Because if you continue use this formula, you cannot explain. You cannot obtain. You cannot explain experiment. So Bohr put what his condition. Oh, what's happened to my pen? So Bohr's condition says it's called the angular momentum. Do you know the angular momentum? Did we talk about angular momentum? R multiplied P?
No.
Okay, must equal to, let's just say, because one electron got a velocity, right? When they got a velocity, therefore they got a momentum. Can you see?
Yeah.
MV. The angular momentum is just R multiplied P, as simple as that, okay? And he said, well, this must equal to the Planck constant divided by 2 pi, or multiplied N. N equal to 1, 2, 3. Can you see?
Okay.
So that is a Bohr's model. Yeah, Bohr model. How did they derive this formula? Now, next, just mathematics. Can you see? Oh, by the way, another thing you need to know is that how about the if I just rewrite this formula, can you see? And that means that the R P equal to MV, right? So therefore we have R. Let's just write down here.
How do you remember so many stuffs?
Well, because my students ask me this question all the time. Can you see? Ask this question. I have many students, so they ask this question. So basically, what they do is, well, if you do it all the time, you remember. Otherwise, you forget. Okay.
So many formulas and constants.
Yes. So therefore, we just focus on this one. So this is just M R V, right?
Yes.
Equal to N H 2 pi. Okay, that is a formula. That is his condition. We rewrite that. We can, if I just we just do some combine this formula. So we need to find the V square, right? This is R multiplied V. So if this is a V square, what can we do? And we can substitute, can we just substitute, we got R multiply V, right? So we, if you multiply V square, how do we solve this puzzle? So basically we need to find the formula for R. Here we got a formula for multiply product of R and V, see? So what can you do? So can we just solve this first? Can we solve this formula? This algebra, can you see R multiply V will equal to NH divided by 2 pi M. Can you follow me? This algebra.
Yeah.
So basically we're trying to use this formula, combine this formula with equation 3. But before that, can we, because our objective is to find what is the formula for R, can you see?
Yeah.
So what is the formula for R? That one we need to know. So this time, if I multiply R square on both sides, can you see?
Yes.
If I multiply R square on both sides, we got the RK E square equal to M R square V square. Can you see?
Yeah.
Then in this way, we can find the formula for R now. Can you see? We divided the K and E square, and we put this K is a Coulomb constant, E square. We got the R V square. Can you see?
Yes.
I think. How about your algebra? Your algebra is okay.
Yeah, I can get it.
You get it. Okay, you can do it now. Can you tell me how to find the formula for R now? You got, can we just substitute this formula here?
Yeah.
All right.
Okay.
Do you want to do that?
Yeah.
So this is this is Bohr's original work.
This is, I can't write it.
You can't write? If you can't,
I can write. I can write.
Okay.
Times V.
Yeah.
And H 2 pi M. And you need to cancel out something, do you?
We can simply replace that. Can we? Because you can see, we got the formula. You didn't notice that. We got the formula for this factor. Let's just use a different coloring. Can you see? We need this guy, and we found this formula from Bohr condition. Can you see? Can we substitute this? We can we can find the formula for R immediately.
So you like substitute the RW
pi, RV. We substitute RV by a Bohr model, okay, by Bohr condition.
Okay. This is so complex. So you need to rearrange this one.
Yeah, we just substitute and simplify. Yes, it's just a simple algebra.
Yes. I think that's it.
Square root?
Yeah.
No. Why do you use a square root?
Because there's a power.
Well, you see, you didn't notice that we got two variables unknown. One is V, another is R. But our Bohr model allowed us to replace it. This time I help you. Can you see? Can I start from here? I just copied this original constant here. Can you see? E squared, and replace this by this formula NH 2 pi M square. That's it, and square. Can you follow me?
Oh, okay.
Do you agree? Do you agree? You got it. So,
yeah.
So this side are all constant. Can you see? So therefore, that is the model. Can you see? And which, if you just continue, Can we put this M outside? M, if you put M outside, that will be Km. Oh, my writing pen. That will be Km E square, okay? And they got another numbers, 4 pi square, okay? And then we got H square, can you see?
Mm-hmm.
And all of them divided by N square. Can you see that?
Yes.
If we call this A, then we got a Bohr model for formula for his radius model. Can you see?
Yeah.
So that is the first Bohr formula. That is a constant multiplied by N square, where N is integer. Can you see? 1, 2, 3. All right. So that is algebra. That's how to derive the Bohr's model. I think in ALTA, you needed to know this method, right?
So that whole thing is called A.
Yeah, the whole constant is called A.
Oh.
Okay.
Yeah.
Because it's all constant. It's a Planck is constant, right? KME is constant.
Yeah.
Yeah.
E
So
is either charge of an electron.
Yeah, E is charge of electron. E is a charge of electron.
Yeah, got it.
Okay. Okay, I think it's good to use algebra. Okay, if you can use algebra, then you can also solve mathematical problem in that test. And the second formula is what is N engine formula. So how to derive the N engine formula here? You see, so N engine formula equal to this one. How to prove that? We just write as a constant here. It's 13.6 N squared. Is that simple? Can you see? So in order to do that, we need to find the kinetic energy first. Can you see? Kinetic energy of electron is equal to half V squared, right? And the potential energy also, that is relevant. Potential energy, do you know how to write a potential energy? Certainly it's negative because it's got attraction. That should be constant multiply E squared divided by R. Have you studied this formula?
No, maybe I did, but I forgot. I just didn't revise well.
Yes, that is just remember this is potential energy. Okay, so therefore the total energy of electron, this is total energy. We are looking for this is total energy. Okay, this is total energy. So the total energy can be written as the total energy.
Add them together.
Add them together. Yeah. mv squared. Take K E squared and R. Okay. But we know the formula for R, but we don't have the V squared. What can we do? So we still can looking for Bohr model, can you see? So Bohr model say, so it's basically equation, or from Newton's, can you see? From Newton's law, we know this formula, can you see? Can we just highlight this formula here? From Newton's second law, can we copy this equation? So that is let's go to the next one. So based according to Newton's law, we know that the K, today not our formula, but we can use this. This according to Newton's law, that equal to mv squared. Do you agree?
Yeah.
So the right hand side looks like the kinetic energy. Okay. So what we can do, if I just divide this by 2 on both sides, you see, then we got a kinetic energy on this side. Can you see?
Yes.
That is how we related this kinetic energy. From this formula, we can argue that the kinetic energy, you see, the kinetic energy is half. Can you see? From here, you can see the kinetic energy is half of this factor. Can you see? E squared K divided by R. What is E squared K? E squared is potential energy. Can you see?
Oh, wow.
Okay. So from here, we can make this argument. The total energy can be written as E is total is equal to half of this term. Can you see? K. Oh, something wrong with my pen. Ke squared R. Take this one. You see? So in this way, we got the formula for the total energy, which is negative because this is half. Can you see? If you just half of that one, can you see?
Yes.
Oh, it's K E squared. Can you see that? Okay, now it's time to substitute our R formula. Can you see? So first, if you go to next one, we need to use Bohr's model now. R is equal to, Rn is equal to A multiply N squared. You see? So in this way, we can derive this. If you know, if you this calculate the formula, if you substitute all constant, we can prove this formula. Can you N here? Important thing is that N squared is here. Can you see? R is associated with N, so this is N squared. So today we just work out how to derive the Bohr's two formula. One is for radiant, another is for total energy.
How did R transform into N squared? Sorry.
Oh, because R, if you replace this R by this formula, if you replace it, we got the R N squared at least. Can you see? So in other words, K, we can argue this K E squared, we put all constant together, all right? And A were
got it.
equal to 13.6, okay? EV, all right?
Yeah. Okay.
Don't worry, Bohr spent 3 years to work out this theory. We only spent a half hour or so, you see?
I think my brain is gonna explode. So many algebra.
Don't worry. This is probably the highest algebra you might use, all right, in the test. Otherwise, the algebra would be simpler than this. Okay.
Yeah.
But doesn't matter. That's why I'm asking you. So the Bohr atomic model is very useful. All right.
Yeah.
They basically explain the absorption spectra. You see, that is how we study atom today. Otherwise, we can never see the size of atom. Okay.
Yeah.
Probably we'll save that. Stop here now. What do you think? If too much theory, we can talk about the example. Okay.
I don't think it's too much. I really enjoyed it because everything's logical to me, and yeah, I just need some revision and I'll understand.
Yes, please, because Bohr model is a very important milestone in history. That's why when they say natural world, they just mentioned two aspects. One is atom, another is the solar system. Okay.
Yeah.
So probably next time we can talk about the solar system.
Okay.
You can read it and digest. Okay.
Yeah.